We're going to continue now with some of our examples on conservation of momentum and also conservation or loss of kinetic energy. So let's take a look at what's going on here. So we have a proton, and we're saying it's 1 AMU. That's the same as grams per mole. And it will make our math a little bit easier. But it's moving really fast, 3.6 times 10 to the fourth meters per second. And it collides elastically with a helium nucleus. The helium's heavier. That's 4 AMU. It has 2 protons and 2 neutrons. That's why it's about 4. If we wanted to take the decimals out a little bit further, we'd see that it's not exactly 4. And then it collides. It's moving in the negative direction. Remember that the positives and negatives are important. Times 10 to the fourth meters per second. Now, if it's elastic, that means momentum is conserved. And kinetic energy is conserved. So we're going to start with momentum. It's always easier or better to start with momentum. So this, I went ahead and just put the numbers in, is really just m1v1 plus m2v2 is, now these are initial, let's put a little I there, m1 v1 final plus m2 v2 final, because they don't stick together. So these numbers are kind of ugly, but that's why we have calculators. I mean, that's all we can do. Be very careful with the positives and negatives. You'll see that the left side collapses down to negative 3.6 times 10 to the fourth when you run all those numbers. Now, I left out the 1 here. I just thought it was easier. We know it's 1. I didn't write it. And I didn't write 4.00. I just wrote 4 just to clarify things. But we should always be thinking about significant figures, especially in a lab situation. That's as far as we can go with momentum. There's nothing more we can do in that situation. So now let's take a look at kinetic energy. So remember, for kinetic energy, it's V1 initial plus V1 final is equal to V2 initial plus V2 final. It's a really long derivation, but we really only care about that equation, that result. And again, that's for kinetic energy conservation. Now, the only thing we can do there is add the 1.8 times 10 to the fourth. Let's add that to both sides. And then we'll subtract the V1 final from both sides. Now, you may need to pause the video from time to time in order to copy. So now we've got equations we can use. We've got this one. We've got this one. We can use systems of equations. We can stack them. So I just rewrote them, and I stacked them. And I really try to make sure to line up my V1s and my V2s as best I can. And this one's really nice. We don't have to multiply it by anything, and the V1's final will cancel because it's positive and negative. So let's see, I add these two down, and I get 1.8 times 10 to the fourth. Maybe we'll put the 0 back. Is 5 V2 final. Then all that's left is to divide both sides by 5. So let's remind ourselves. The proton we said was M1. And initially, it's going in the positive direction, and the helium's going back. And that's M2. So this is initial. because it is important to understand what's going on. And then for the final, the helium's going to bounce back, just like two pool balls colliding. So we kind of suspect that the proton's also going to bounce back in the other direction. Let's see. So what I did there, and let me clean off some of these notes just to make it a little easier for you to see. Get rid of these. All I did there is I went up and I got another equation. I got the one with the 5.4 in it. So 5.4 times 10 to the fourth plus V1 final is V2 final, and I have that from here, so I substituted. Then I just subtract 5.4 times 10 to the fourth from both sides. And I get 5.04 times 10 to the fourth meters per second, but it's negative. So they collide here in the middle, and they bounce back away from each other. Now let's do one where they stick together, and I have this little graphic here that I found, this little GIF that shows them sticking together. So I think that's great. So we have an 1,800 kilogram Cadillac. That's a really big car. And it's hitting a car that's about half of its mass, only 900 kilograms. Oh, okay, no, the small car is hitting the big car. I was wrong on that. So the small car hits the big car. Now this is a stick-together problem. So kinetic energy is not conserved. This is what we call perfectly inelastic. I just think about the real important point is that they stick together. So the small car is hitting the big car. So this formula is actually pretty easy. And in fact, since the Cadillac is stuck at the light, it'll be 0. Oh, I call the Cadillac M1. That's fine. Call that M1 and get rid of that there. And M2 was the other car that was moving. Let me clean that up for you a little bit. There we go. Sorry about that. And now it's actually pretty easy. It's just adding stuff together and calculating a V final at positive 6.67 meters per second. And I think it's important to remember this too, that before, here's the little car, and there's the big car. Before the momentum is in the positive direction. So after the collision or final, the momentum still has to be in the positive direction. They won't be going as fast because the Cadillac is heavier and now the overall mass is heavier, but the momentum has to be forward. So an interesting question, at least to me, is how much kinetic energy is lost in that process. So we're going to have to calculate the kinetic energy initial. So if we remember, initially, only the little car was moving. The big car, the Cadillac, was stopped. So its initial K is 0. Only the little car has initial kinetic energy. So the little car had, this is just 1/2 mv squared, just to remind ourselves of the kinetic energy formula. So 900, 1/2 900 times 20 squared is a big number, 180,000. Afterwards, they were stuck together. The little car is 1,900 and the big car is 1,800 kilograms. So overall, because they were smashed together, is 2,700. So we see that kinetic energy is lost in this collision. It's not conserved in an inelastic collision. So we can easily subtract the two numbers and get how much is lost. We're also often interested in, well, what percentage is that? What percent of the initial kinetic energy is lost? So percent is part over whole. So the part that we lost, and we're going to just take an absolute value because we're just saying this is the percent that was lost. We generally put what was lost over the initial or the starting kinetic energy. So when you're getting these percentages, it's generally the starting or the initial kinetic energy that you put on the bottom in the denominator. And it's important when we look at these numbers, we're not just getting numbers. We can program a computer to do that. We have to look at it. So we look at that number 67, that's 2/3. 2/3 of the kinetic energy is lost in this collision process. That's quite a bit, and that's not unusual for these kind of collisions to lose that large amount of kinetic energy. So let's try another one here. It's kind of maybe a silly example, but we have two balls of mud collide and they stick together. I guess it's the two political sides throwing mud at each other. I won't name any names. So we know the mass of one, and it's moving in the positive direction. And the other's going in the negative direction. Now, we haven't yet calculated the momentum, so we don't know if there's more momentum in the positive or if there's more momentum in the negative. We just haven't figured that out yet. I think we could eyeball it and see it looks like there's more momentum in the positive direction, but let's see. So we want the final velocity of the balls after collision and the percent of kinetic energy lost. And do they stick together? Yes, they stick together, so we can use the stick together formula, and that's actually pretty quick. It's not that difficult of a formula to use. So we start to put some numbers in, and we're very careful about our positives and negatives. Now we get positive 1.67. We should always look at numbers and say, do they make sense? Let's see, 0.5 times 4 is 2, I believe, right? Yep, positive 2. That's the momentum going in this direction. 0.25 times 3, or negative 3, is negative 0.75. And that's in the negative direction. So the initial momentum, 2, is bigger than the negative 0.75. It's going to win. Overall, the final momentum, when they've stuck together, has to be in the positive direction. And with that speed of positive 1.67, it will be. So now we've got to get the kinetic energy, percent kinetic energy lost. So the first order of business is we've got to calculate the kinetic energy's initial, and we've got to calculate the kinetic energy final. Remember that both are moving. So initially, there is kinetic energy for both of them, and we add it together. Now, the energy for the one that's moving in the negative direction won't end up being negative, because negative 3 squared is positive 9. So the kinetic energy will be positive for both of them. There usually isn't negative kinetic energy. You don't think about it that way. Now, afterwards, they've stuck together. So their total mass is 0.5 plus 0.25. That's where the 0.750 is coming from. Yeah, and just like we saw with the cars, it looks like we lost some kinetic energy. It looks like we lost quite a bit. So we'll subtract, and that should be joules, And just a reminder that whenever you have delta, it's always final minus initial. Always. We use it for temperature in chemistry, temperature final minus temperature initial. We use it all kind of places in physics, V final minus V initial. It's always final minus initial. Then to get the percent, we put what was lost. Oops, that should be negative there. All right, let's put that negative sign there. But we're only going to worry about the absolute value over the initial. And we lose about 80% of the kinetic energy in this process. That's quite a bit, but that's what the numbers tell us.